right, here we go.
Good morning, ladies and gentlemen. Do this now in the Barbie lab. We sent light from plastic into air. What angle of incidence would produce a refracted ray, a refracted angle of 90 degrees?
Gonna need to use Snell's law. Now the trick here is, what is the incident material? What's the refracting material? And the key is, from is incident and into is the refracting. So it's going from plastic to air.
Okay, so give it a shot here. Pause it.
Pause, do this.
Okay,
Right.
and now that you guys are done, I'm gonna go and work through it here. So we said it's going from plastic, right? And so that's gonna be, this is gonna be plastic right here, right?
Yeah, don't forget
And
to put the theta in.
Oh
for-
shoot, I forgot it
That
too,
was what I
Boykin.
did.
Okay, I get too excited about writing the word incident. Okay, and then we're going into this, and what are we trying to actually find?
The angle of incidence.
We're trying to actually find this. So I'm just gonna start off by dividing by this.
Yep.
Okay, my angle of incidence here. And then, so now I've got this right here, refracted over the index or refraction of index. That's an R. Okay, and then I'm just gonna go ahead and do the inverse sign here.
Yep.
Okay, and I'll put that in parentheses, and that's gonna give me the angle of incidence. Okay, so now again, we gotta be careful here. We gotta make sure we put in the right things. So this one is from, what was the number associated with from over there?
No, that's 2. The refracting is air. The refracting material is air, so that's 1.0003.
Oh wait, we sent light from plastic into air? From plastic into air?
Yeah, so refracting material.
Sure. Look at us refracting.
Yeah.
Okay, so let me go. I'm just gonna put it right down. Actually, I'll put it over here so I have a little more space. So this is the into, right? We said, and so that's 1.3, right? And the sine of this
90
one is 90.
degrees.
Yep. Okay. And then what is our incidence here?
That's the plastic.
That's the from. Okay, like that, and then we just have to take the inverse sign of that, right? Okay, plug her in. Okay, so the inverse sign, I'm gonna say 1.3 times the sine of 90, close that parenthesis, divided by 1.5, close my parenthesis there. I get 41.8.
41.8 degrees would be the angle of incidence that would produce an angle of refraction of 90 degrees. Now that's measured from normal. That's 90 degrees from
Yes.
normal.
Yes.
How you guys doing? You getting this?
How we doing? How you doing? Okay. Turtle and tonal reflection. You guys see that reflection up there? On
Cool.
top of the water? We're gonna talk about today.
Turtle.
Turtle. Okay. Principles of optics. Things happen at surfaces. Yes, they do. Normal is a line perpendicular to a surface at a point on the surface.
Yep.
And here are our definitions. Our incident is our incoming ray to a surface. Reflected bounces back from a surface, and our refracted bends passing through a surface. Everything happens at the surface.
Yep.
Okay, and of course we have our law of reflection. Our incident angle is equal to our reflected angle, and this is measured from the normal.
Yep.
The angle of the incident ray equals the angle of the reflected ray.
That's right. It's a
Okay.
mouthful.
Refraction. Light bends when going from an incident material into a refracting material, like from plastic to air, air to plastic.
This sounds suspiciously like review, Ms. Mo.
It is review. Okay, so the index of refraction relates to how much light bends when going from one medium to another. We're gonna take out the book and show them that table again, Boykin. 397. 390. Oh, almost there. Oh, wait. 397. Oh, no, wait. And here is our table of refraction. And so we said it's a relationship to how much light bends when going from one medium to another. So greater incidence. Did I say angle? Greater index of refraction means more bend.
That's
like
right.
in diamonds. Yikes. Okay. Snell's law. We already used this today.
Yeah.
Right, we're familiar. Just don't forget your angle. And you saw me get kind of like twisted there. You know, make sure we know which one is the refracted, which into, from, because you get it back.
You got to get the players right. You know, once you get to the math, it's simple.
Yeah. Okay, which way does light bend going from low to a high index?
Here's an illustration going air into glass.
Air into glass. And you can see as it comes in, it's bending toward that normal.
Yep.
Okay. Now, do we want to go into the math behind this? Or
That's up to you.
We'll keep going. Okay. Which way does light bend going from high to low? Now, this picture is a little bit confusing because we're going this way. We've been going down through this the whole time, but here we're going from water. Oh, was the last one water?
It doesn't. No, it doesn't
No,
matter.
it wasn't. Okay. But still, same thing, right?
It has a higher index of refraction than air.
We're going from water. Typically, it would just go straight, right? But since we have a change in the properties of the medium here, it bends away.
Yeah, and that's like if here we have little Nemo here, and Queequeg with his harpoon wants to. If you aim right where you see the fish isn't there because light comes from the fish, bends away from the normal towards the eye. So you have to aim low if you expect to have something for dinner.
What a nice visual. Nemo. I love that movie. Okay, what is the maximum angle light can bend away from the normal?
Well, if you have a surface, the normal is 90 degrees away from the surface. If it bends more than 90 degrees, it's not, it's
not refracted
No,
anymore.
in fact, that reminds me of, what's the next slide?
Here we go. So a ray refracted at 90 degrees from the normal goes along the surface, and we call it the critical ray. So the answer to our previous slide, what is the maximum angle that light can bend away from the normal? It's 90 degrees because we have an angle here. Okay, we've got this ray coming in, and then it says a ray refracted at 90 degrees from the normal. That's 90 degrees from the normal.
Yep.
Oh, sorry, excuse me. Well, no, 90 degrees from the normal, right? Goes along the surface.
And like in the What's the Matter with Barbie lab, we came in we started at a shallow angle, and the ray was bending away from the normal. As we increased that angle, it bent more and more away from the normal, and it can't bend any more than 90 degrees. Otherwise, it can't get out of the glass.
Do we want to show this to them yet? I think this is helpful.
Yeah, I think so.
Okay, so here we are going
I'll
from.
go on the other side.
Okay, so here we're going from water into air, right?
Yeah.
And normally it would just go straight, right? But we have bending at that surface because we have a change in the different indexes here.
Yep.
Okay, so we're bending away here. Now, as we move this angle out more, right? We're moving it from here, and moving it out more like this. At some point, that angle, that ray that's coming out is actually going to go along the surface. It can't make it out anymore. This angle is getting bigger. Okay,
And if you increase it anymore, it can't get out at all.
And what do we see here?
A reflected ray.
Okay, so to be continued. In the Barbie lab, we sent light from plastic. Okay,
Well, that's that Do Now. That's that same thing we just did.
Yeah. So in the Barbie lab, we sent light from plastic. So this was from plastic into air. Okay, into air over here.
Yeah.
What would be what angle of incidence would produce a 90-degree refracted ray?
And so that's what we did. We plugged in 90 degrees for our refracted ray and ran it through Snell's law and came up with
41.8, which is, I believe it's 41, degrees on the Barbie lab or something like that, right? And so what we had at that point was a critical ray. So I've got some pictures here. So in order for a ray to pass through the surface, it has to be less than our critical angle, which we're going to talk about in a second. Okay, so this is the angle we're talking about right here, measured from the normal. Our incident ray coming in, and at this point, it's less than the critical angle. This angle right here is less than the critical angle. So it makes it through.
It can get through the surface.
Yeah. Now, at this point, this is the critical angle. And notice how we're getting a little bit further out here?
Yep.
Okay, so we've hit the critical angle. At that point, the light has bent 90 degrees, and now this critical ray
Goes
is
along
going
the surface.
along the surface, okay? Now, what happens if we move it even further, like in our Do Now Barbie lab?
Yep.
Okay, we move it even further. Now it's beyond the critical angle, and we have no light making it through the surface. It's all being reflected, total internal reflection.
Should we look at Barbie?
We should. Okay, here we are. Okay, so here is Barbie, and you notice that there's something funky going on.
And the question is, where is Barbie's in a fish tank, and where is the surface of the water striking Barbie?
Well, where do we see that reflection happening? Right around here, right?
Yep, because she's got two pairs of hands.
Yeah.
She's got two crotches, and so the water level's right there.
Yeah.
And what we're seeing here is this is where the water level is hitting the edge of the fish tank.
Uh-huh.
And so the image of Barbie that we see up here is reflection off the surface.
Cool. All right, so critical angle here, when the critical ray comes in, we get a critical, when a critical angle comes, how do I say, was that right?
Critical angle comes in,
When you've
it's
got a ray that comes in
refracted
at a critical
along the
angle.
surface.
Yeah, when you have a ray that comes in at the critical angle, it's refracted along the surface. Anything more, we get total internal reflection. Okay, the angle of incidence that produces a refracted critical ray is called the critical angle.
So, and that critical ray is 90 degrees.
Yes, it is. Along that surface. All right. Is it time? Yes.
Well, here's this example. Yeah, let's do this.
Oh no, this one right here, or which one? No, I think we're just gonna talk on this one.
Yeah.
Okay. So right here you have the light going straight through. It's right along the normal, so we have no refraction, right? Now the normal. Can you see it okay?
Yeah.
So our normal is right here. Now you've got a ray coming in at some angle to the normal, and we get refraction.
Yeah.
Right? It should go straight right here, but it bends away. Now we've got light coming in at a little bit more of an angle here, and you can see that we have some refraction through, but we also get a little bit of reflection.
Yeah, it's getting closer to 90 degrees.
It's getting closer to that critical angle and getting closer to that 90-degree
So
refraction.
less of the light is going through, and more of it's being refracted. Reflected, I beg your pardon.
Now over here we have surpassed our critical angle, right?
Yep.
Because it's all reflection.
Can't
No
get
light
out.
has gone.
And thank you, Russell Kitely.
Yes, awesome, excellent. Now 396.
I don't like that.
No, that's a good-
This is good enough.
Okay. All right. So an incident ray greater than the critical angle can't get through the surface. That makes sense.
Yeah, that's what we're seeing.
And this results in total internal reflection.
That's what it's called. Total internal reflection.
And you can see how that we get that reflection above. All of the light rays being reflected off of this that are creating this reflection up here are because they're greater than the critical angle.
Yeah.
Yes. Okay.
But if it's a turtle, it's turtle internal reflection.
Yes.
Physics joke.
Turtle and total reflection. Okay. And now for the
Laser. Let's turn the light up.
Lasers. Laser. Okay. All right, so here we have our piece of glass. We've got our laser beam, and as I shine it straight through, it goes straight through, yes?
Yep.
Okay, now what happens as I slowly but surely move it through?
See where it's hitting her thumb there? Keep going. And bang. And now it's coming out.
Yeah.
Now it's coming out. And so what happens is and then take it back out. Now it's beyond the critical angle. The light stays inside and comes out the other end. It can't get out.
And we'll mix it up here. We'll go for this guy. Okay.
And see the light stays on the inside. Now there you can see where it's hitting. It's what we went to. There's the critical angle right there. And then once you're beyond that, it stays inside.
Okay, and then you've got really cool things like this.
And this is the optical fiber. The laser this is the principle of an optical fiber. The light goes through the optical fiber and bounces around but can't get out, and it comes out the other end.
Can't get out. Trapped. Help me. Okay. Cool. Down with that. All right, and then here we have you guys, it's getting hot out. Have you guys ever been in the pool before? Have you ever jumped to the bottom and like held your breath and like looked up at the top? And then you kind of see this like bubble of the sky, right?
Yeah.
But then outside of that bubble, in this case, it's the ceiling here. Outside of that bubble, you see the floor of your pool.
Yeah, and so from your eye to where that the outside of the bubble is, actually the circle is less than the critical angle.
Yeah.
And light can get through. However, if you're outside the critical angle, you're seeing the reflection of the bottom of the pool.
Yeah, so, as you look through the middle here, it's just straight through, and then you get a little bit further out, light's bending more and more and more and more and more. And then at some point, right here at the very edge of the circle here, that's when we are, the light that we are experiencing right there is beyond that critical angle, and it's all being totally reflected.
Yep.
Okay, so, boom, that's it. Oh, we got homework. Okay. So regular physics book today, ladies and gents. We're going to have a quiz, if not tomorrow, the next day. And this is going to be on chapter 17, page 411. You're going to do these problems.
Actually, it's 411, 412, 413. It starts on 411.
Starts on 411. Okay, good luck.